Thanks for coming. Welcome to reInvent. So this is CON306, building machine learning infrastructure on Amazon EKS and Kubeflow. My name is Yaniv. I'm part of the container services team at Amazon. I've been working at Amazon for over 4.5 years. Most of this time was spent talking to customers such as yourselves and helping you guys build workloads on containerized applications, on workloads like, on services like Amazon EKS, ECS, Fargate, and AppMesh. And I'm also honored to be here with Jean-Marie and Jeremy from Babylon, who's going to talk to you about what they're doing in machine learning and what their company is trying to build as a platform with Kubeflow. So we're going to cover some basics on what is the Amazon ML stack, and then why people are leveraging things like Kubernetes as their platform for running machine learning and end-to-end machine learning platforms. And then we're going to talk about Kubeflow. And Kubeflow has been one of those technologies that emerged more than others over the last year and a half, and kind of walk through some of the modules that Kubeflow has that allows data practitioners, data engineers, data scientists to get an easier way and easier access to a bunch of tooling related to running machine learning workloads. And then I'm going to hand it over to Babylon, and they're going to talk about how they actually already applying all those things on top of Kubeflow and some of the do's, don'ts, and best practices involved. So just going quickly over the Amazon ML machine learning stack. So we have a 3-layer stack in which we provide each of you data practitioners a machine learning capabilities based on your preference, based on your skill set and your knowledge and familiarity with machine learning. So at the bottom layer of the stack, for those of you who feel they have vast knowledge in running machine learning workloads themselves, picking up the best-of-breed frameworks for them to run, and choosing among our broad array of compute services and instances, whether it's CPU-based or GPU-based. You can choose from all of these and run it yourself. At the middle layer, we have SageMaker with all its surrounding services, and I'm pretty sure at least most of you have heard yesterday's announcements, expanding and significantly extending the number of services and capabilities that SageMaker offers. And that's kind of a fully managed service that gives you the option to run your machine learning frameworks without having to worry about any of the underlying compute infrastructure, but still requires you to be a data practitioner or a data scientist that knows about how to build models, how to train models, and kind of wants to go through that machine learning lifecycle. And at the top level of the stack, that's for programmers and developers that don't necessarily have the skill set to train models or create machine learning models, but still want to be able to kind of embed machine learning capabilities into their own application using Amazon's trained models. And so for those, we have a bunch of services around recognition and transcribe and forecasting and other services that help you get all those machine learning capabilities, even though you may not be a data practitioner or a machine learning practitioner yourself. So over the last year and a half, ever since we launched EKS, we have started to notice that a lot of teams and companies start to run their machine learning services on Kubernetes. And so when talking to them to kind of understand what drives them to run those machine learning services on Kubernetes, we kind of came to the conclusion it's about Kubernetes as a platform and the benefits that you get by running other workloads in your application on Kubernetes apply here as well. So things like portability. You may want to start your work on your laptop or on your desktop GPU, but then as your machine learning models become bigger, the data sets become heavier, you may want to kind of move that over to the cloud and enjoy being able to dynamically provision resources on demand. So that's one use case. Other use cases may require you, and you'll hear from Babylon, companies that have a global footprint and may want to deploy that machine learning stack everywhere, right? Including locations that Amazon is even not deployed in yet, like Africa. So for those kind of use cases, it's efficient and it's very valuable to have a stack in which they can port over from one place to another. Kubernetes is also composable in the sense that you can actually create what we call custom resources on top of Kubernetes. And that's merely a way for you to extend the basic Kubernetes APIs with your own. And a lot of the frameworks that are running on top of Kubernetes, such as Kubeflow, are heavily relying on that capability to implement things like pipelines and other features as well. So like I said, a year and a half ago, we launched Amazon EKS, which is our managed Kubernetes service. And what Amazon EKS gives you first and foremost is a fully managed control plane in which you can bring in your clusters, create clusters of Kubernetes, and have us basically create and manage all of the API servers and all of the etcd persistence layer. All of those control plane components are being created and also being managed by Amazon in a secured, in a scalable fashion, and also in such that allows you to bring in your worker nodes, which you have full control over. Now, to extend that, over the last couple of weeks, we have made a few announcements related to managed node groups and also supporting Fargate as an option to run EKS workloads as well. And that also kind of extends that manageability portion to your worker nodes as well. So you can now also have Amazon manage your worker nodes, upgrade the Kubernetes versions, or patch your worker fleet as needed, or even switch to a completely serverless abstraction running Fargate pods by switching to that compute mode. The other thing is we provide a completely upstream native experience, so we're not forking Kubernetes in any way, and if you have workloads running elsewhere on your Amazon account or even outside of Amazon on your own premises or other cloud providers, those workloads can be ported over to EKS back and forth. Third, we're a platform to run enterprise and production-grade workloads. So EKS has been doing really well. The platform has gone up 10x in usage over the last year. And so we have a lot of large companies and enterprises that are using and leveraging EKS for a very broad array of workloads. And as I said, machine learning has actually been popping out as one of those big ones that have been emerging as customers start to run their pipelines there. And we also provide integration with other services, and I'll mention a few of those, like the CSI drivers for storage, ALB ingress controller, and other components that allow you to basically leverage other parts of the AWS ecosystem along with your Kubernetes workloads. And I will say that a lot of these integrations are not just unique to EKS, but they're being upstreamed and also available for you to run Kubernetes on AWS, whether it's co-ops or a self-managed cluster. So which type of users are we catering to when it comes to machine learning? So basically, we see two main use cases. One is if you're the data practitioner, and the other one, as these companies and large companies want to extend the footprint of how they're leveraging machine learning because it's becoming a commodity and actually something that a lot of companies want to leverage as a way to get better insights on their business, there is an increasing need for those to kind of set up operation teams that can support all these data scientists and data science teams that need to kind of collaborate with each other, consume resources, including GPU resources, which may be more expensive than CPU ones, and kind of provide them with kind of a platform that can offer all of that as a service. So that's why we're seeing a lot of those teams, and I think those two different audiences have different needs. So let's talk about that for a second. So on one hand, we have the machine learning practitioners, and so often cases, data scientists and such do not necessarily want to be exposed to all the details involved in setting up EC2 instances, knowing what a VPC is, EBS volumes, and so on and so forth. They just want a very quick and easy way for them to deploy their machine learning workloads on something that is more abstracted. And so they're looking for a platform, any platform, to basically offer that. A bunch of APIs or a nice GUI that can give them a way to visualize, train, prototype, and then take that model all the way to production. And then the end-to-end portion is one of the key points there because we see a lot of collective tools, and Kubeflow is no exception to that, giving you capabilities to train models and prototype and run ML inference, and I'll cover all of these, but there's also the glue that needs to kind of stitch all of those together to one holistic pipeline, and that's something that we find, or we find our customers to find very useful for them to be able to set up like workflow mechanisms to bring that model from one stage to another in an automated fashion. On the other end of the scale, there's also a bunch of, I would say, ML-related tooling like hyperparameter tuning or things like feature engineering. And those are specific tools, and experiment management is another example of that. And those are specific tools to machine learning, but those machine learning practitioners would still like those platforms, if possible, to offer those tools as an added value in addition to all the basics of doing training, prototyping, etc. Now, the ML teams or the operation teams that need to support these data science teams, they need to come up with a platform that can serve all those purposes. They need it to be as abstracted as possible, and they need to be able to segregate and provide permissions to those teams to consume resources. And for that, they would need authentication. So they need to know which team or individual is looking to get resources, what kind of operations or resources they can consume, and based on that, they can actually manage the platform to the benefit of everyone in the company. So with that, I want to kind of walk through what Kubeflow is and how that kind of helps getting all those objectives done that I just mentioned. So Kubeflow is one of those open source projects heavily relying on Kubernetes. It's part of the Linux Foundation. And it's a project that has emerged more than others. And it provides you with a collection of tooling. And that's first and foremost what Kubeflow is, a collection of machine learning tools and APIs for you to be able to run your machine learning workloads. So I'm going to go over some of those tools. But if you want to look at kind of what the map is, Kubeflow looking like today in terms of features, that would be it. So Kubeflow is built in a pluggable way. And again, being based on Kubernetes, it gives you pluggable mechanisms. So for each of those things that you're looking to get out of your machine learning process, for example, ML inference, there are a few options that you can plug in at the moment and more that could be coming tomorrow. So that's kind of one of the benefits that Kubeflow offers is the pluggable mechanisms. And I'll walk through some of the model serving options, and I'll walk through some of the training, how most of our customers are doing training, and how do you do prototyping using Jupyter notebooks. But it also comes with a few of those additional tooling. So for example, there's a project called catib, which is used for hyperparameter tuning. For those of you who doesn't know, hyperparameter tuning is when you have some parameters that are external to your model, like how many iterations you want to run and so on and so forth, and you want to experiment those same models using a variety of values for each of those parameters. So ideally, you would take 1, 2, 10 parameters, and you would run those machine learning trainings using a range of values for each of those parameters, and then you would ideally want to have some visualization of, okay, based on the parameter values, what was the run that gave us the best accuracy? And you would take those parameters, and based on that, that would be the values that you're promoting to the next stage. So that's just one of those features. So talking about prototyping, often cases when machine learning practitioners start to prototype, they first and foremost go to notebooks and Jupyter notebooks specifically. Now, for those of you who are not familiar, Jupyter is a technology that's been around for quite a few years, but haven't actually started from machine learning use cases, but more from big data, analytics, and data cleansing. And so we have seen customers bring in live code, train the models inside their, or if it's a data cleansing job, they can just run an ETL job within the notebook itself. So the job would be fetching data that resides on S3 or any other location, process that ETL function, and then show you the results. Now, because Jupyter is very pluggable, you can also bring in a lot of different visualizations, graphs, and one of the best features of that is the ability to share and collaborate with other people on those results that you're seeing in your notebook and on the code that you're working on. So that's one of the reasons why Jupyter has emerged for all these use cases, and machine learning was one of those other use cases that have emerged as a good way for the data scientists to prototype on the code, quickly run a training job, maybe a small scale, and then as they go more confident, they can send the large-scale jobs to the next stage using a very dedicated set of compute, and I'll cover that in a second. It's also very extensible and supports a variety of programming languages, and so all of these make Jupyter a very good fit for running. And when you're installing Kubeflow, you're getting a Jupyter Hub server installed on your Kubeflow deployment, which means that you're basically getting a URL that you can just paste in your browser, and you'll get the Jupyter Hub interface, and that'll allow you to create different notebooks and start collaborating and sharing. One thing to point out is that from Amazon's perspective, we have launched the support for EFS, which is Elastic File System, which means that if you have this live code, it's very easy for you to share that code with other people because it's on a shared file system, as well as the fact that if, for whatever reason, the underlying pod that's running your notebook is crashing, you can actually persist your notebook into EFS, and then as you're bringing that pod back up, you can actually restore that same notebook that you were working on without loss of data. That's agnostic to the fact that you can also have the actual data set that you're working reside somewhere else and have the code just point out to that. So you're still required or should be using best practices like saving your code in a code control, source control version system like Git, saving your data in places like S3, and also kind of integrating with that. But the mere code of the live notebook that you have can be persisted to EFS in addition to that. So once you're done with your prototyping phase, now is the time for you to kick off training jobs. And like I said, training jobs can be kicked over inside the notebook itself. But often cases, what we see is for the larger use cases, and especially as it relates to deep learning, which is a specific subset of machine learning, which is more complex and usually requires larger data sets, that's often cases a time where you want to bring in some larger set of infrastructure and GPU instances to kind of help process and get through the training job faster. Now, one of the areas that we're seeing that more than others is the autonomous vehicle space. So if you look at the traditional autonomous vehicle company that needs to kind of process a lot of data that's being ingested from the car and all the cameras, that data obviously needs to be ported over to the cloud for that big data and machine learning processing. But then after processing and pre-processing and cleansing the data, you would want to kick off a training job. Now, one of the ways that allows us to significantly reduce the time it takes to train a deep learning model is what we call distributed training. And so distributed training is merely the ability for us to use multiple GPUs and maybe across multiple EC2 instances in order to almost linearly, not linearly, but almost linearly, reduce the time of training as much as scaling up the number of GPUs. And so one of the challenges there was, how do you make sure that your code that was designed to run on a single GPU can actually run on those multiple GPUs with minimal code changes? And so one of the frameworks that we saw customers using over the last year or so was Horavad in order to get that done. And so Horavad is a framework that allows you to have a very easy API to really take your code, which was built for a single GPU, and with very minimal changes, change that and work on multiple GPUs across multiple nodes. So the way that that works is we're using a component that Kubeflow offers that's called MPI Job. And MPI Job merely takes your machine learning code or model and spreads that across all of the nodes that you're running. Now, once you have that algorithm within each of your nodes, Horavad kicks in and uses an internal communication, a lower level communication library called Nickel, which is the NVIDIA collective communication library, to actually do all that parameter exchanges between all those running GPUs. So for example, if you have 8 P3 instances with 8 GPUs each, you actually have a grid of 64 GPUs that Horavad can actually leverage, and using an internal algorithm called ring all reduce, basically make all those distributed training, exchanging of parameters in a very, very efficient way. Now, and one of the things that also happen is you stage your data first on some local or shared file system on your cluster. So typically, you don't want to train the data and have the nodes read that from S3 directly, but copy the data first to some location. And that location can be either an EFS file system, but it can also be something newer that we launched a year ago, which is called FSX Luster. And FSX Luster is a high-performance shared file system that gives very good throughput for multiple nodes and multiple processes that are reading the data all concurrently. And so that makes it very suitable for those kind of workloads. Now, the benefit of using FSx cluster is that you only pay the penalty for copying the data once. So copying a large set of data for deep learning can take minutes and sometimes over an hour for very big jobs. And so you probably, especially if you have a platform that can have multiple jobs kick in, won't want to pay that penalty all over again for every job that you have. So copying that data to FSx cluster and keeping it there will allow each of those training jobs to just leverage that existing data without having to do that copying all over again. Secondly, FSx cluster also allows you to relay an S3 bucket. Now that means that you don't need to even explicitly make a copying of the data from S3 to FSx, but you can just provision FSx with an S3 bucket, and that will basically trigger off a relayed copying of the data as those nodes are starting to read from that file system. So you're actually using FSx cluster as kind of a caching mechanism for you to be able to efficiently run the jobs. If you want to know more about how to run distributed training jobs using Horvad and MPI Job on EKS, there's a pretty nice blog written by one of our principal SAs, and you can actually access that QR code from here. That'll give you also a step-by-step instruction to actually set it up. I will add, however, that there are other ways to run distributed training. So if you're running TensorFlow, for example, TensorFlow does have APIs to do distributed training using something called parameter servers. At least as of the TensorFlow 1.x version, we have found that to be less efficient than the Horvad implementation. But TensorFlow 2.0 was announced a couple of weeks or a few weeks ago, and so that equation may change over time. So once we have established a training job and we have now obviously done some iterations, so training results may not be what you want, so you'd have to kind of perform a few iterations of those, and we'll get to the pipelines component soon. But at some point, you will have a model that you feel ready and accurate to deploy to production. And so how do you deploy inference? So there's a bunch of ways. One of the ways that Kubeflow offers is a native way called Kubeflow inference, or KF serving. So KF serving is basically a way for you to deploy an endpoint that your applications can then hit in order to do inference requests against the model. Now, it's relying on a cloud-native stack that includes Knative, which is a technology that allows you to run serverless applications on Kubernetes, as well as Istio, which is a service mesh. And in this case, Istio is being used to set up the gateway by which you will hit that application with a certain URL. And obviously, the whole thing is relying on Kubernetes. Now, one of the things that were important when designing KF serving was, like we said earlier, data practitioners don't necessarily know containers. They don't want to be exposed to the underlying technology or the infrastructure, but they do want to be able to use multiple machine learning frameworks, which is what they do know about. So the first thing is KF serving supports multiple frameworks like scikit-learn and TensorFlow and PyTorch. But also, if you look at the way that they will provision that ML inference, it's pretty generic, and it really ties into the way that data scientists store their models. And the typical way for them to do that is just serialize that model into a file. So what KF serving allows them to do is just specify a simple path for where their model file resides, and that component takes it from there, deploys all the relevant components, and basically sets up that serving endpoint that can then be used by the applications. With that, I want to move over to end-to-end machine learning. So by end-to-end machine learning, I mean, how do we connect the dots between all those pieces, right? We know how to prototype, we know how to run training, we know how to run inference endpoints. How do we take it through a workflow engine or a pipeline? So one of the additions that Kubeflow has made later on in 2019 was Kubeflow pipelines. And Kubeflow pipelines relies on a workflow engine called Argo, for those of you who may know this. And Kubeflow pipelines is merely a way for you to create a pipeline which is composed of steps, whereas each of those steps can be any one of those things that we mentioned earlier, or even custom code that's being executed, and create dependencies and define what are the inputs and the outputs of each of those steps and the connections between them. Now, if you look at the way that each of those steps is being configured, that's being formed in a way that has metadata associated, so you can bring in a bunch of parameters, and you can also have parameters injected into the pipeline YAML that you're creating. But each of those steps is being implemented by a Docker container. So for example, if you wanted to create the training job that we mentioned earlier, you would be creating the Docker container that actually implements the training code and then pointing to that from within your pipeline. And the pipeline is merely a Python script that's basically a definition of all the steps that that pipeline contains. And once you're done creating the pipeline, that thing will get compiled into a YAML file, which will then get packaged and will then be able to be served by Kubeflow and be run by the platform. And so one of the things that the machine learning team at AWS have started to think about since Kubeflow Pipelines was launched was, is there a way for us to allow folks like yourselves or others that want to run Kubeflow or Kubernetes as their machine learning frameworks, but also be able to kind of leverage the AWS innovations wherever it makes sense? And so today the answer to that is yes. So this week we announced on what we call SageMaker Kubeflow pipeline components. And those are merely pipeline components compatible, so you can run them within your Kubeflow pipelines, but they are implementing or kicking off SageMaker jobs and allow you to run SageMaker capabilities such as training, model generation, the hyperparameter tuning option that we have within SageMaker, which is not catib that I mentioned earlier by Kubeflow, but one of our own, and then batch transformation and model deployment as well. And so the SageMaker team will keep iterating on that and may add to those capabilities that exist today, new capabilities that the team introduces over time. If you want to know more about that, so there's actually a session today at 4 p.m. by that product manager designing that feature, and he can actually dive deeper and give you some more details about what the value proposition is and how you can leverage that with your machine learning applications. So kind of talking a little bit about what we have next before I hand it over to Babylon. And so Kubeflow is still not a graduated project. It's been worked upon significantly and has gone through major steps throughout 2019. And the community is now kind of targeting Q1 and hopefully January as kind of the target for the 1.0's announcement. So, and the big theme for the 1.0 would be more enterprise-grade features. And that probably ties into things like collaboration, multi-user support for the pipelines and for your dashboards in general. So be able to use the Kubeflow dashboard between multiple teams and multiple users. And then from our end, we will also introduce things like a recent capability that we launched this year, which is the IAM roles per service account. So just to explain what that is, if you have a pod running which accesses other AWS services, that capability allows you to attach an IAM role specifically to that pod or group of pods under a specific service account in Kubernetes, and only those pods would get those permissions, whatever they may be, whether it's accessing an S3 bucket or an RDS database or anything else. So we want to embed that capability into Jupyter notebooks so that you can have granular pods getting granular permissions as an added value for that when you're running it on AWS. So what are the key calls for actions for you? So first, if you want to know more about Kubeflow, you want to get your hands wet, there's actually another Kubeflow workshop. We had a first run this week on Monday, and then the next run of that would be tomorrow at 3:15 p.m. And that's where we actually give you like a guided tour of how to set up Kubeflow on EKS, running through some of the models that I mentioned here. And actually, for those of you who can't make it, we also have an online workshop, which is what we base our workshop on. So you can actually take it in your convenience at home or at your office. So this is the URL for you to access that workshop. And please let us know how it's working out for you. And if you have any feedback, it's an open source workshop, so you can actually open issues, pull requests, and anything else that you'd like. And finally, if you want to talk to us, we have a Slack channel in the Kubeflow Slack, which is the AWS Slack channel there. I'm there, and so is all of the EKS product managers, deep learning engineers, and all of the stakeholders within Amazon that are involved in this project. And we'd love, and so are other customers that have actually started to build their platforms on Kubeflow. And so if you want to talk to these customers, you want to talk to us, ask questions, have suggestions, anything else, please feel free to join that Slack channel by picking up that QR code. So thanks so much. With that, I'm going to hand it over to Jean-Marie from Babylon.
Thanks, mate. I need to switch off here. Thanks, Yaniv. So we are Babylon. We are a company on a mission. Our mission is that we believe it is possible to put an accessible and affordable health service in the hands of every person on earth. What does that mean? I quite like starting by the end, the fact that we do that for every person on earth. So it's not a system that we're designing for few people, it's a system that we're designing for many. We currently have more than 3 million users. And we do that in a lot of countries. So we operate in the UK, in Canada, we're going to soon launch in the US, but also Yaniv was talking about it in Rwanda and in the Kingdom of Saudi Arabia. So in all these geographies, accessibility and affordability come together. There's no point having a really accessible service if it's not affordable. So what does it mean having an affordable health service? If you get it from the payments perspective, in a health service, 2/3 come from the cost of healthcare professionals. If you get it from the disease perspective, 2/3 of the cost comes from managing predictable and preventable diseases. So that's really where the focus of Babylon is. It's about automation and prediction. So how does that translate into our product? We essentially have 3 main products. One is Health Check. So Health Check is a product that you engage with when something is wrong. So you've got a symptom, you've got something that is not going quite well, and then you'll have a conversation, and it will take you through a journey and bring you some ideas, some reassurance on what's going wrong with you. You can imagine AI in that kind of use case is absolutely essential. We've got another product, Monitor, which is a lot more ongoing. So you go in and check in whenever you feel like about your mood, about how you feel, and then it will give you real-life ideas to make your healthcare better. The largest product that we currently use is consultations. So consultation, you can think about it as FaceTime your GP. So it's not FaceTime, it's our own, you do that within our own application, but the idea is the same. So having access to a GP really easily. I'm going to show you now what we'd like the GP portal, on the other hand, to look like. So it will be a video, but you'll see there's a lot of AI in there as well. So the whole thing is about helping the doctor, giving him the information to come to a diagnostic quicker, to come to a more informed diagnostic.
Hi, Louise. My name's Dr. Kultag Archer. Nice to meet you.
Hi, nice to meet you too.
So I can see you've completed our AI assessment. And from this, can I confirm that you've been having dizziness for a few months now with some hearing loss and also some ringing in your ears?
Yeah, that's right.
Okay. You look quite comfortable at the moment. So does the dizziness come and go?
Yeah, I don't have it at the moment.
Right, so that's what we want the experience to be for the physicians. So in terms of the challenges that we've got as a company, we're currently more than 1,600 people, and a lot of our challenges can come under the masthead of being a global operation. So when we build our products, we don't want to build products which are for a specific location. We want to build products which are global. So how do you do that? How do you build AI flows that are local enough that they're relevant for a specific country, but global enough that when you do an improvement, that applies across the board to all our geographies? Then the second point about global is just something that all of you are in companies that are scaling up our experiences, which is just a matter of scale. We now have offices in the UK, in London. We've got offices in Austin, in Texas. As a company, we grow, we explode. How do we structure ourselves? How do we make sure that we stay relevant, that we stay nimble in the way we approach engineering. And the last one is about the platform itself. So we operate across the world. How do we keep one platform which is relevant for everyone? How do we go into geographies where AWS might not be present, for example? So to put that in perspective, some numbers. So currently, we've got more than 300 microservices in production. We do more than 500 deployments to production on average per day. And we've got more than 15 EKS clusters deployed across more than just 5 AWS regions. So in the context just of AI, what are the main challenges that we've got? One is about providing a safe and secure environment for our research team. Again, that's all with medical data, health data. So that's data which is highly secure. We only want to give people access to the data when they need to for a specific use case. It's not about, as an engineer, you can access all the data. You will have to have a reason for why you need to have access to a specific data. Then data locality. A lot of the time, because of the regulation of a healthcare industry, we can't take the data out. So again, how do we do that? How do we have one team, or maybe one team in the UK, one team in Austin, that is building the models, but then training these models in country because we're just not allowed to take the data out of the country. The third point is about the fact that we want to train and manage our AI model at a global scale. So all about the data lineage. Under GDPR, we need to be able to track the data that was used to train specific models. How do we do that at a global scale? We don't have the luxury of having just one target platform. And the last one is what I was talking before about being a global operation. We've got to maintain the efficiency. As we grow, we need to make sure that our velocity is not impacted, that we actually go faster rather than going slower because we're bigger. On that, I'll let Jeremy talk about the solution that we've implemented.
So, I'm Jeremy. I'm an infrastructure engineer at Babylon, and I'm part of the team that manages our Kubeflow setup. So, Jean-Marie talked about improving engineering efficiency, and this is why the team I work on was created. And the idea was, machine learning is a complex thing to achieve, and there's a lot of hidden complexity around how do you manage the infrastructure, how do you manage the data, and so we wanted to centralize that effort and provide a self-service platform to all of our engineering teams to make them focus more on the machine learning itself rather than the infrastructure. We had some requirements for that platform that we wanted to build. So again, we are in healthcare. Healthcare needs to be secure all the time. And even though this was more of a training platform, we wanted it to be as secure as production. So we would treat that platform as a production platform. We also wanted it to be scalable. And that's not only scalable as in different countries, but also scalable as in if I am running massive machine learning jobs, I want the platform to scale to as many nodes as I need. And when I'm not running anything, I want the platform to scale down to 0 because I don't want to spend too much money, especially in the cloud. We also wanted that platform to be flexible. And what I mean by flexible is we wanted it to be modular so that we can deploy new tools on top of Kubeflow, on top of Kubernetes, that we'll need for the right job. So we're big believers in building using the right tool for the right purpose, and so we wanted the platform to allow us that. And finally, again, we're a global company. We operate in many countries, so we want that platform to be global. We want it to be portable. If we need to deploy it in a country where AWS is not present, we need to be able to do that. And so using something like Kubernetes as the base infrastructure layer allows you to do these sort of things. And so this is typically what a cluster for machine learning on top of Kubernetes would look like. So you start with your base infrastructure, which is AWS for us, and then you would deploy Kubernetes. On top of this, if you need to control the network, you can use a service mesh. And finally, you apply all of your AI toolkits, so Kubeflow and maybe other services that you built internally. So this is what it looks for us as a cluster. And what I'm going to do now is I'm going to walk you through some of the things that we had to solve and some lessons that we learned along the way. And hopefully it can help you if you're working on building these kind of platforms. I'll start talking about the infrastructure and the networking of the platform, and talk about some of the workloads we use. And then I'll talk about how we manage Kubeflow within that platform, how we add more projects on top of that, and how we manage the way our workloads are going to run. And finally, I'll talk about once those jobs are finished and the models are trained, how do you manage the deployments of those models? Okay, so let's start with the infrastructure of EKS. So there are a couple of things that to keep in mind when you're doing that. The first thing is for a machine learning pipeline and machine learning platform, you want different type of nodes. People are going to need different hardware. Maybe some users will like GPUs, some others will need a high CPU throughput. And so you need to make sure that the platform will be able to support all of this. So what we do is we create different autoscaling groups, and one autoscaling group per type of node. So if you need also different type of GPUs, you can add different autoscaling groups. One other thing that's very important for us was encryption. So we wanted everything to be encrypted by default. It's very easy to encrypt EBS volumes, for example, on AWS. But one thing that we learned is that you also want to encrypt the AMIs that are going to run. That's not on by default, so if you use the base EKS images, they won't be encrypted. So you will need to use a tool like Packer, which is an open source tool, to harden the node and then push it back to AWS with a KMS key to encrypt it. And that's very important because when you run Kubernetes, your containers, if you don't specify any volume by default, will run on the root volume of that node, and that's what the AMI uses. So if you don't do that, actually most of your workloads won't have encrypted volumes. And finally, make sure that your API is private. It's very easy to enable on EKS as well. And also your nodes needs to be private, so make sure you put them in a private subnet. GPUs are getting easier and easier to manage on EKS. What you need to do is just install a simple daemon set that was created by NVIDIA. And so that daemon set is going to check if the node is actually a GPU node. And if it is the case, then it will register it to Kubernetes as a GPU node. So the scheduler can then push the GPU workloads to the right node. Another thing to do, though, is when your node is going to spin up, you want to taint them. At least that's how we do it. The reason is you don't want non-GPU workloads to run on GPU nodes for cost efficiency. So if you taint them and then you add a toleration to your jobs that are going to run, then you can make sure that only GPU workloads will run on that. And if you use different type of GPUs, so P2 and P3, for example, you can label those nodes and use the accelerator selector on Kubernetes to choose which GPU you'd like to use. So this is one example here of what it would look like on a YAML manifest. Okay, so networking. We see two different kinds of networking for the platform. So the first thing is the base layer of the networking, which is the VPC. So we have private subnets. If you can, spread around multiple availability zones. I think 3 is a good number or more. Some zones, some regions, don't have still 3 zones, but it's preferable if they have. And another thing we realized is you're going to have some issues with the cluster autoscaler if you don't provide one autoscaling group per node type per AZ. Because the cluster autoscaler on Kubernetes is not very zone aware, so sometimes you'll have some issues where a disk is being spun up in one place, an EBS volume, and a pod is being spun up in another zone, and so they can't connect. So make sure you have one ASG per AZ. And we also use NAT gateways for accessing external endpoints on the internet as well. And then comes Kubernetes networking. And so here you have a lot of flexibility. You can use things like service mesh to control the network, and this is what we wanted to do. We wanted a way to, by default, block any traffic between different pods and operate a zero trust policy on the cluster. And if a service needed to talk to another service, we could manually, or at least automate it, but at least we specify that we wanted it to be the case. So by default, no network would work. And we also wanted to encrypt all of that communication with mutual TLS. If you are in a regulated environment, that's sometimes mandatory. But using service mesh as Istio, this is what we use. There are others like Linkerd or Envoy. These kind of service meshes allow you to do that, and it's actually quite useful. Okay, so I personally think that Kubernetes is a great platform to run machine learning workloads. It scales very well, and you can actually run your apps and your models close to each other. But when it comes to machine learning, then Kubeflow is really the best toolkit for Kubernetes out there. At least that's what I think. What we love about Kubeflow is that it's very modular, so you can pick and choose the right tool and the tool that you need. So Yaniv presented all the different tools you have on Kubeflow. We actually use a subset of those. So what we do is we just decide which ones we're going to use and we deploy them on the platform. And since this summer, accessing some of the Kubeflow UIs has become a multi-user. So you can plug it to your enterprise IDP, and people can just register and log in into, for example, a Jupyter notebook. We use a lot of Jupyter notebooks at Babylon. We also use training jobs, so TensorFlow or PyTorch, and we are big users of hyperparameter tuning as well. There's been a lot of questions about how you actually deploy Kubeflow on Kubernetes. Kubeflow provides a CLI tool, KFCTL, and it's going to deploy the whole toolkit. It's very easy to get started with this tool, so that's what I would recommend. But once you get a bit more advanced, you might want to pick and choose the right tool. So what we do is we use customized manifests, which Kubeflow provides, and then we generate a massive YAML file that describes all the features that we want out of Kubeflow. We push that to GitHub, and then we have our GitOps tool called Flux that will pull those changes and apply it on the cluster. So the deployment of Kubeflow and actually every other workflow we run on Kubernetes is entirely automatic. So there's no human interaction on the cluster, which reduces errors. And also GitHub acts as the auditing layer for everything that we deploy, which is very convenient for us. So we can know exactly who deploy what and when. Now, another thing to keep in mind when you start running workloads on Kubernetes is you have to understand how they're going to work. And for us, we wanted to isolate some kind of workflows. And we came up with the concept of a project. So everything that runs on the platform will be part of a project. That project is basically a Kubernetes namespace with some role-based access control rules that will control who can access that namespace. And then on top of that, we would add EFS volume, so an EFS partition, so that every single project can store results, models, and different type of files directly on the EFS and then find them back later. So for example, with Jupyter notebooks, it's very convenient. You can just save your work and then shut down the notebook, and the next day you spin it up and you have your work again. Namespaces on Kubernetes allow you also to manage the quotas. So if you want to restrict by default how much CPU or memory a project can use, then you can do that. And also if you need more like faster storage, you have other options such as EBS or FSX for Lustra. Right, this is a part I like. So when we created the platform, we had a lot of feedback about, we need visibility on what's running on the platform. And we are a big fan of Prometheus and Grafana. We've been running it for a while now. So we wanted to use the same thing for managing our machine learning workloads. And you can imagine it like from both ways. So from the user, you want to know what's going on in your project. So every project comes with an automated dashboard where people can see how much CPU they are using, how much memory, and all the pods that are running. But also for people like me in more the MLOps space, you can actually see how your cluster is behaving, and that's also very convenient. You can see if it scales properly, this sort of stuff. But one important thing that actually came up very early in the process were the users were telling us, okay, it's really cool, like I can run this on the cloud, infinite scale, but how much is it going to cost? Like I want to know exactly how much money I'm spending. So what we see here is highlighted. We actually have a third-party tool that tells us a bit more about our cost on AWS. And we built a small application that would get those data and export it to Prometheus so that we can show it to the users as well. So now each user can see exactly how much money they spend on the platform. And we also have a leaderboard for the most expensive project. If you want to deploy Prometheus and Grafana on Kubernetes, you can. Actually, I would recommend that. It's very convenient, and you can automate your dashboards with Kubernetes config maps. So again, same thing as before, you can push that to GitHub, and then it will be automatically applied, and you don't need to restart Grafana or anything. The dashboards are automatic. I mentioned extensibility before. So this is one example where it was earlier this year, actually, back in January, February, where we wanted a way to run workloads and pipelines on the platform. And so we came across this tool called Argo, which is a cloud-native tool for running pipelines on Kubernetes. And we deployed this next to Kubeflow to try to run the clinical validation of our main machine learning models on the platform. And we had this issue where one of our flagship model really was taking a lot of time to validate locally. I won't go into too much detail, but basically it was running on bare metal servers. It was very long, and it usually takes about 10 hours to finish, so people will do some changes, wait until the next day to get the results, and it was a very painful process. So we took the opportunity to take that clinical validation and port it to Kubernetes with Argo. And by using some parallelization where we deploy the model like 30 different times in parallel, and then we have our script querying it, we optimize the script, and we managed to actually reduce it to 20 minutes. And now the team is now looking at putting this validation job at every pull request for those model changes. So the feedback loop for the users has decreased massively, and it's taking only 20 minutes to get the results. So you can see that people are able to iterate faster, and that eventually leads to a better model, a safer model for everyone, which is great. Okay, so this was pretty much like the stack of a single cluster. I mentioned before that we wanted a global platform. So one cluster is not going to be enough. We need a cluster in every region we operate. So what we did is we actually designed a way to schedule all of our workloads on different clusters around the world. So you can see here we have 3 clusters, one in Asia, one in Europe, one in America. And we have this API layer with the DynamoDB table for keeping some state, like who is a user, what's a project, what's a resource, and what's a region. And then the users will use that API to just say, okay, I want to train that job in the Europe cluster, for example, or the US cluster. One of the good things that this API provides is also simplicity of use. For those who use Kubernetes before, or even Kubeflow, actually deploying workloads can be a bit complex. And when people don't even know about Docker, sometimes it can be very hard to get started. So this is one example. You can see on the right side, this is what a pod that needs a GPU node and needs to attach the EFS volume would require. And this is quite complex. This is a lot of lines of YAML for very little actually information. It's necessary complexity for us, but not for the users that are going to be using this. And there are some issues where, for example, if you make a mistake with the indentation, for example, your resources won't be accepted by Kubernetes, or rather it will be accepted, but Kubernetes is not going to take it into account. So we had issues with that in the past. So what we did with this API is we actually simplify the interface for the user, where the user can actually just specify what they need, which is, I have this Docker image, I need to run that script, I need to run on this kind of node, and that's pretty much it. So we take that information, convert it into a Kubernetes manifest, and then we take care of running the job. Right, so for the last part of that section, once we have trained all of our models, we need to deploy them. And at Babylon, we deploy our models exactly the same way as we deploy any type of microservice. So we have this centralized tool that we developed. It's called Shipcat. It's written in Rust and is open source if you want to check it out. And that tool is a deployment tool for Kubernetes that we like to call SDLC-aware deployment tool. And what I mean by that is that when you deploy a service using that application, you're going to specify so how much memory and CPU it needs to use, all this kind of stuff, but you also specify what kind of compliance or regulation the service needs, if it manages data, what kind of data, so we can then track what service is using what data. It also gives links to engineering documents and all kinds of other informations that allow us to keep track of everything. And once this is done, we can, as a user, I can just say, okay, I need to deploy this application with the model in these and these regions, and then the tool just goes and deploys it on all of our Kubernetes cluster. So that's it for my part. I'll give it back to Jean-Marie for the next steps.
Thanks a lot. Thank you. So you've heard a lot about what we've done so far. What are the next steps? The thing that we want to focus on for the next quarter or maybe year. So the first thing that we want to focus on is build a common model serving framework for Babylon. Again, it speaks towards our efficiency, the fact that we're global and we want to grow really fast. We also currently track metadata, but we want to track more metadata to be more comprehensive. You've heard about Argo, the fact that we've plugged that in addition to Kubeflow. We want to start using the Argo, which is coming with Kubeflow itself. And you've heard about the fact that not everyone is an engineer. We've got data scientists that need to use that platform. So the experience of using that platform is also key. We want to make it easier for people to adopt, to reduce cognitive load so they can focus on the data science rather than the plumbing that goes under that. Thanks a lot. Don't forget to rate us, give us feedback. Thank you.